As you may know, the second Sunday of each month we have a Science Sunday thing here. In December we had one about astronomy, optical astronomy, and in January, she didn't finish in time, so we're doing a second part in January. Get closer, like that. Is that better? Okay, all right. Thank you. So,
lean back and let me turn it up here a little bit.
Is that better? Better for me? Keep talking. A, B, C, D, E, F, G, H, I, J, K. Like that?
Take a step closer to the podium, but don't punch forward.
How's that? Is that going to work? Perfect. Okay.
I just don't want you ruining your bag.
Thank you. Thank you. Okay. Okay, so in between optical astronomy in December and again in November and again in January, there are other windows on the sky, other ways of seeing things from the sky. And that's what I'm going to be talking about today. And so all sorts of things fall from the sky, but up until not long ago, we only knew, well, one big rock's coming with, actually death of the dinosaurs, that was an asteroid that came in, spewed ash and earth and stuff around the world and the dinosaurs after millions of years of rain. That was the end of them, except the little ones that stayed and became birds. So the birds are the descendants of the dinosaurs, the ones that survived. And then in the middle you see common little things, shooting stars, which you've all seen, right? Shooting stars. Total misnomer, because they're not stars, they're more like grains of sand that come in from space and they burn up in the atmosphere, leaving a trail of hot gas, which you see as a training through. That picture, I got it from ChatGPT, actually. There's two things wrong with that picture, at least. It's a picture of a girl looking at shooting stars. And one thing wrong is that you don't usually see several at once. You see one and then another one later. And I was out seeing the Perseids and counting about 13 over an hour. And then they come in from the sky. People didn't know what they were, shooting stars. But now we know they're little things like grains of sand, or sometimes pebbles that reach the Earth and can be found. And if you want to find this, then you find them easily in Antarctica, where they lie in the snow. Anyway, then there are trillions and trillions and trillions of teeny tiny things coming in from the sun. They're particles, protons, and light nuclei coming from the sun, hitting the atmosphere and lighting it up by making the atmosphere fluoresce or glow in different beautiful colors. How many of you have seen an aurora? Most of you. Good. Okay. So they have been seen as far south as here. Especially they were seen as far south as Texas, when there was a giant flare from the sun, a coronal mass ejection. I'll tell you about that. But then, so these are trillions and trillions of particles from the sun hitting the atmosphere and making it glow, different colors coming from different excitations of nitrogen and oxygen. But I'm not going to talk about those more. These new windows on the sky. So at the top there you see the spectrum of electromagnetic waves. And you see a little tiny thing there. For the far left is long wavelength radio waves. The far right is very short wavelength gamma rays. And in the middle, there's the visible spectrum. On the left, you have the deep red, and then it goes green, indigo, violet. On the right-hand side, you see the ultraviolet, which will give you a tan if you get too much in the sun, or burn your skin. But that's the window we had to look at space until not so long ago. I put there a couple of pictures of I got All the Light We Cannot See, which is a novel you may know. It's about a blind girl as in the French resistance in the Second World War. It's a very good story, actually. So basically, I put that there because all the optical wavelengths longer than red are infrared microwaves, which heat up your food in the box, and then radio waves. And for the far left of that, there will be electromagnetic waves with much longer wavelengths, even kilometers wavelengths that we haven't detected yet, because the atmosphere is opaque to them. But there is a project called DSL to go in space and detect these very long wavelength electromagnetic waves. The limit, you'd have an electric field that goes up and down and up and down, and we've never detected those, but it will be interesting. The DSL project, I've forgotten what it stands for, is doing that. On the right-hand side, you see the very short wavelengths, or high-energy photons, gamma rays, that come from the sky, and I'll talk a bit more about those. So there's a lot of the electromagnetic spectrum that we didn't have access to until we had radio telescopes and detected microwaves from the sky. I put this here because they're nice pictures of the sun at different wavelengths. To the left of the slide, you see the visible light spectrum from red to violet, and these are all ultraviolet pictures of the sun. On the right, you see the shorter wavelengths of gamma rays, and at different wavelengths, you can see the sun with different images of the various activities on the sun. So that's a pretty picture, but this is all optical, with ultraviolet here, actually. But then in the galaxy, when you look out at a galaxy, you can now look in many different wavelengths. It's all optical astronomy. Far left is in ultraviolet. Far right is in... far left is in radio. The far right is in ultraviolet, and then X-rays on the right. So in X-rays on the right, you see the high-energy X-rays coming largely from the center of the galaxy. It's not our galaxy, it's another one. We can't see ours from outside like that, of course. But you see, when you look at the galaxies in different wavelengths, from radio, microwaves, optical, ultraviolet, and X-rays, you see different structures, and you learn an enormous amount about the galaxy from this. This is all optical electromagnetic waves, from radio to gamma rays. At the bottom, I put another row there, which is about neutrinos, because neutrinos come from the sky, and I'll say how they were discovered and what they tell us. The far left is the various low-energy neutrinos that we haven't yet detected, but they should come from the Big Bang. And the Big Bang would have produced lots of neutrinos, but as the universe expanded, they got less and less energy, their wavelengths were stretched, and now they're probably impossible to detect individually, but cosmologists say they should be there because they're part of the mix of things in the early universe, and if they weren't there, then that would change the cosmology. So we haven't detected individual ones, but we're pretty sure they should be there. Then on the far right, you have neutrinos from supernova, the very highest energy ones, from a supernova and a blazar, and I'll say more about that. So the bottom line here is about not electromagnetic waves, but neutrinos coming from the sky, and I'll say how they were discovered. And so this is about the aurora. The aurora comes from, it's called the solar wind. This diagram, lots of criticism on this diagram, of course, but it's just a sort of sketch. The sun is really vastly bigger than the Earth. In fact, and it radiates, of course, the solar wind in all directions, but that which comes to the Earth hits the magnetosphere, the magnetic field of the Earth, and the stuff that gets through, going towards the north and south magnetic poles, then lights up the sky with these beautiful auroras. And underneath, at the top there, the solar wind gives these auroras, but also cosmic rays with not trillions and trillions of very low energy ones, but even individual very high energy ones do the similar thing by making a trail of ionization light in the sky. Light flashes in the sky. And those are the ultra high energy particles, protons and light nuclei coming from the space. Here's a beautiful picture of the aurora, and I saw it up in Lapland. That was great. I saw it in Stockholm, but Lapland was really amazing. You lie on the ground and you see this show going on for hours. It's really amazing. So then cosmic rays were discovered by Victor Hess, who we knew there was radiation because if you had something charged like an electroscope, it lost its charge. So seemed to be radiation around here. Where was it coming from? Was it coming from the Earth or from up in the sky? And he did an experiment in 1912. He went up in a balloon flight, and he found that when he went high up in the atmosphere, the radiation increased. So it wasn't coming from the Earth, it was coming from above. That was cosmic rays coming in from outer space, and he discovered that way. After which, over the decades, people studied this more, taking so-called cloud chambers up in the mountains. This is one up in the Alps, and this is a gas which can show trails of ionization when droplets form on the tracks of ionization. This is a picture of a cosmic ray coming in from the top. It hits, there's a load of lead plates there to increase the showering. The cosmic ray kicks electrons out of atoms, that is, ionizes them, and then they make more and more and more, and you get a whole cascade or shower of electrons and positrons, which are positively charged electrons. So that's a little shower. That thing is about 0.5 meter square. Took it up in a balloon, or 3,000 meters. That was up on a mountaintop, actually, in the Alps. So there you can see that one particle coming from space can make a whole shower of other particles. It has enough energy. The energy is converted into new mass, E is mc squared. Energy goes into matter in the forms of electrons and positrons. So then, let's look more at these very high energy individual particles coming in from space and making a shower in the atmosphere. So this is an image, well, it's a reconstruction of a shower from an ultra-high energy cosmic ray coming in from space, hitting the upper atmosphere, and starting to make a shower of other particles, not just electrons and positrons and photons in this case, but also protons, pions, all sorts of particles that come down and they make a huge cascade that spreads over a large area on the ground. What you see there schematically on the ground is a lot of little elements which are actually spaced over a large area. There are 500 detectors covering 300 square miles, because when these showers reach the ground, they can spread over many square miles, and you can detect them by putting detectors in an array. And I'll show another one, the Auger project in Argentina. On the left, you see in the window there a sort of telescope that's looking at the sky, and on a clear, dark night when there's no moon, you can see that flash of light. It's like a mini aurora, but it lasts for milliseconds as the particles are coming in at nearly the speed of light. Little flash, like a mini aurora, but from one particle and not trillions and trillions of them. So that's called a fly's eye detector. And it can see, so when you see these particles going into those detectors on the ground, they make signals that you collect, and from the timing of the signals you can get the direction of the shower, and you can, on a clear dark night, see the streak of light in the sky, and that tells you where it's coming from in the sky. To see if it's coming from an object like a black hole or something like that, that you can identify in other ways. So here's a sketch of how a shower develops very high up above mountain altitudes. And this is a single proton from, I call it GKW, God knows where, we don't know where, and shower of billions and billions of particles hitting the ground. And then the energy of these particles is way much bigger than anything we produce on Earth. The highest energy particles we produce on Earth are at CERN in Geneva, the Large Hadron Collider. It's 16 miles around. We accelerate protons in both directions to about 0.999999 speed of light, crash them into each other. But these particles have much more energy than those even. So I comment, no black hole made. When the Large Hadron Collider was starting up, some people said, "Don't do it, you might make a black hole and suck the Earth in, and that would be the end of us all." And actually, they forced a serious study to show that it wouldn't happen. And one reason you know it's not going to happen is because there are much higher energy particles coming in from the sky. At the top end of the spectrum, there's about 1 per square kilometer per century, but in the history of the Earth, there's been many, many centuries, many square kilometers, it hasn't happened. And we haven't seen other planets being sucked into black holes either. So that was not a real worry. Or my next door neighbor, when it started up, she said, oh, thank you for not making a black hole. So now this is another cosmic ray project, the Auger project in Argentina. Auger was one of the discoverers of the high-energy cosmic rays, showers. He discovered the showers they make. And at the bottom you see a sketch of all these things are water tanks, like the size of a backyard swimming pool, but closed in, so no light gets in. And the water then, when the particles come into the water tank, they make flashes of light in the water. It's called Cherenkov light. And those flashes can be detected by photomultipliers, light detectors. And then when you have, these tanks are a mile apart, and a big array covering 3 times the area of Chicago, actually, on the ground. So it's a huge particle detector. And it only detects samples because one backyard pool every mile is a small sampling of the shower. But from the timing, you get the direction where the shower's coming from in space to about half the size of the full moon on the sky, a quarter of a degree or so. And then at the same time, like in the previous one, there's this fluorescence telescope looking out and seeing the flashes of light in the sky when it's a dark moonless light about 15% of the time. So I was part of this project in the beginning. On the right there is a picture I took of Jim Cronin, who started this project. He'd already got the Nobel Prize in physics for discovering the asymmetry between matter and antimatter. He called it CP violation. That's another story. But then he had the ambition of making a huge cosmic ray detector to find out where these things are coming from in the sky and start cosmic ray astronomy. And I was down there at the very beginning. We had a meeting down in Argentina. I was part of it for a few years. And my contribution really was saying, look, these light detectors, we can put them around, 3 of them around the periphery, looking inside, so we don't have to look all around all 360 degrees, just look inside, and then we can detect them. I couldn't stay with the project forever because I had other jobs to do. But now it's gone on from strength to strength, only in the southern hemisphere. And now this is, on the right, you see a graph, which is, on the vertical scale, the energy, every tick is a power of 10. So I see on the left bars, this doesn't work for laser, but million. So from 10 to the 3 to 10 to the minus 27, that's 10 to the 30 powers of 10. This spectrum of cosmic rays. The ones very far left, the very low energy ones, the very far right, the flux is so low, it's like 1 per square kilometer per century. So how do you detect them? Well, you build a detector 3 times the area of Chicago, and you get a few a year, and then they're the most interesting ones because they're such high energy that they don't get bent around by the magnetic fields in the galaxy. The lower energy ones do get, when they come from far away in space, they get bent, the tracks get bent by the magnetic fields, and you don't know where they originated from. But these very high energy ones, you can trace their path on the sky because they don't get bent much by the gravity, by the electromagnetic fields. And that's a map they've made of very high energy cosmic rays, and you see a cluster there around a special part of the sky which is starting to see a point source. And so you're starting to use these cosmic rays for astronomy, but it's very tough because only the most energetic ones actually point back to where they started from. But neutrinos are different because neutrinos come from these very energetic events in the sky too, and they have got no electric charge, so they don't get bent by magnetic fields. So if you see a neutrino coming from the sky, you can point out to where it came from and start to do neutrino astronomy. And there's a whole spread here. On the left, you see a picture of the sun in neutrinos that I'm going to explain. And then the supernova, the Crab Nebula, which was a supernova. Yes, sir. You'll need a microphone.
How do you know there are trillions going through your little finger?
I counted them. And I count 5 fingers, so I multiply by 5. But this is, okay, the next slide may explain it. Okay. All right.
Oh, wait.
Yes, Sterling. Because they're so weakly interacting that they go right through you, the trillions through your finger, and in your lifetime, 1 or 2 may interact in your lifetime, but normally not, because they go right through the Earth. They come out from the center of the sun, without interacting with the sun. And to detect them, we have to go generally deep underground to shield us from rubbish like low-energy cosmic rays. And so that's, now we're studying neutrinos now. We make beams of them at Fermilab, but we have to make extremely intense beams of protons, smash them into a target, make other particles that decay to neutrinos. And we've got this project that we're sending neutrinos through the Earth, 800 kilometers to northern Minnesota, where we've got a huge detector down a mine to detect neutrinos coming from the Earth. But that's a different talk. These are ones coming from the sky. And you'll soon see how they were discovered coming from the sun. Okay. On the right, I've got the cosmos. We haven't discovered neutrinos in the Big Bang yet, but we know they should be there. How they were discovered, how they're found. This is Ray Davis's experiment. He had a brilliant idea. So, of the nuclear reactions in the center of the sun that have been worked out in the 1930s, and you can calculate how many neutrinos should be emitted from the nuclear reactions in the center of the sun that give us the energy and eventually the light that we get and the heat we get from the sun. So from the amount of light and heat you get from the sun, you can calculate the number of nuclear reactions and therefore the number of neutrinos you should get. And this guy, Ray Davis, said, maybe I could detect those neutrinos, because when one of them hits an atom of chlorine, a nucleus of chlorine, the neutrino can change the chlorine into an isotope of argon. It basically changes the neutron. So the neutrino plus chlorine should go to argon plus a positron. But the rate is so low, you expected several a week in this huge tank of, chlorine. How do you get chlorine cheaply? It's cleaning fluid. So he made a huge tank of cleaning fluid down a mine, actually, and to shield it from cosmic rays. And he said, every week there should be a dozen neutrinos detected by turning a chlorine atom into an argon atom. And how do you detect the argon atoms? Well, it turns out those ones are radioactive, and you can flush them out. Concentrate them, and measure the radioactivity of the argon that comes out. And that's counting the argon atoms that were created by that process. So that's a decay of argon back to chlorine. And so he did this, and he did detect, he detected a few a week. Actually, more like 1 or 2 a week. But it's a puzzle, because he should expect 3 times more. And that remained a puzzle for a long time. He had to keep working on not saying, I must have made a mistake, go away and do something else. He kept at it. And the theorists who calculated the reactions in the sun kept at it. And eventually the problem was solved. He was detecting about a factor of 3 fewer neutrinos than were emitted by the sun. And the reason is because the neutrinos change their flavor. Anyway, here they come. Here's a picture of the sun. The center of the sun is where the reactions occur, and the neutrinos are produced there, and they come out through the sun. They can get through the sun, no problem. They can get into your detector deep underground, because they get through. Only 1 in a trillion actually will interact in a big detector. It depends how massive it is. I'll show you some more. But on the right, you see another neutrino detector called Sudbury Neutrino Observatory. It's in Canada. It's down a mine in Canada. And they built that vast spherical tank and filled it with heavy water. Wow. And they detected neutrinos from the sun, and they detected all neutrino types. There are 3 types. I won't go into that in detail, but we found there are 3 types of neutrino. One goes with the electron, one goes with the muon, which is a heavy version of the electron. A third one goes from the tau, which is an even heavier version of the family, electron, muon, tau. And on the way from the sun to the Earth, they mix up, so by the time they get to this detector, only 1/3 of them are electron-type neutrinos that Ray Davis detected with his chlorine. The other 2 could also be detected in this big tank of water, and they showed that they measured 2 things, a total neutrino flux of all flavors and the electron neutrino flux, and showed a factor of 3. And this is a big project at Fermilab, understanding how neutrinos mix with each other. So then we go on to Japan. Under a mountain in Japan, there's a Kamiokande Neutrino Observatory. It's under the mountain, so you can drive in through a road. That shields you from a lot of the cosmic rays that were discovered before. And on the right, you see a picture of inside this huge, huge tank, which is going to be filled with pure water. You see 3 men in a boat there, or 2 men in a boat, working on these. Around the whole inside of the tank are these photomultipliers. They're light detectors. They're this sort of size, and when light hits them, they send an electrical signal to the computers upstairs. And when a neutrino comes in, sometimes it can interact in the water. Most of them go straight through, but some of them do interact, and they make particles which give flashes of light in the water, and the flashes of light are detected by all these photomultipliers. And then, from the pattern of the light, that on the right you see every point there in that picture is one of these big photomultipliers, and the ones you see in green there are lit up by light signals coming from this shower. It's in a ring. This is Cherenkov light. Now, what that is like a sonic boom, but with light instead of sound. When an aeroplane goes supersonic, goes faster than the speed of sound in air, it makes a sonic boom. You can hear it. And the same thing happens with charged particles going through a medium like water. They come in nearly the speed of light. They don't slow down, but the light slows down. So the light in water is slower than it is in air. And that makes like a sonic boom, but with light, which makes a ring of light on these photomultipliers. Little diagram of how it happens there. So Cherenkov light is called after Russian Cherenkov, who figured it out. You can actually see sometimes in a nuclear reactor that's water-cooled, blue glow in the water, which is this light of electrons in the water. But that's another story. So when you measure these, you measure the time of a signal in each photomultiplier, and you measure the position, and from that you can figure out the direction the neutrino came from when it interacted in this water. And then you get those directions from these events. They're quite rare. You get one every so few hours or something. And you plot them where they came from on the sky, not where they came from on Earth. And then you can reconstruct the image of the sun. This is the sun at night. Night, day, it doesn't matter for neutrinos. They go through the Earth anyway. But if you just looked at night, this is actually building up the signal. But at night you see the sun. It's actually a fairly bit smaller than that glow, because the resolution is not as precise as your eye. But that is a picture of the sun using neutrinos at night. Okay. And so, John, another, as seen through the Earth, yes. So this detector that made this picture is under the mountain in Japan, and it detects neutrinos coming from upstairs and downstairs in all directions, because they come right through the Earth, and most of them go straight through the Earth without it interacting at all. But when you have so much mass, you have, a cubic meter of water weighs a ton. So when you have, a cubic kilometer, that's 1 billion tons of water. That's a lot of target, and you need that sort of massive target to detect these things. And I'll go on to see more of these. These are ones from the sun, so they're low-energy neutrinos from the sun, from nuclear reactions. But we can do more astronomy than seeing the sun. We knew the sun was there, but this allows you to understand better the nuclear reactions in the sun that power it. So this is a busy slide, but it shows lots of things where neutrinos come from the sky. On the top right, you see a banana. Bananas are radioactive, right? You can put one up and they get occasional clicks because of potassium-40 in the banana. But that particular banana was that banana was sold for $6.2 million, and with a certificate saying it's the original banana. But when it rots, the artist will give you a new one to put in. Isn't it crazy? It's crazy. Yeah. I don't know who bought it. Somebody who thought they could sell it for $7 million later on. I don't know, but it's art market gone crazy, right? So now supernova. This is pictures of the Crab Nebula. So the Crab Nebula was discovered a long time ago as a little fuzzy thing in the sky that looked a bit like a crab to Earl Ross, who discovered it with his telescope in Ireland, I think it was, called it the Crab. But this is the Crab Nebula in different wavelengths of light. Well, X-rays at the top, visible light, infrared bottom left, and radio on the right, you see it looks very different in these different wavelengths, which enables you to understand it. But this is all in electromagnetic waves, okay. And I can't read over there, but you can maybe read the caption. So the star exploded 7,500 years ago. The light took a long time to get to us, and the light was seen as a flash of light, a new star in the sky in 1054 AD, thank you, just before the Normans invaded Britain. And the light flash was detected by astronomers in China, Arabic, Korean, Japanese. The main people know about the Chinese one because they documented it very well, but it was seen, it was bright enough to see in the daylight, I think, the supernova. Star explodes and gives a huge flash of light for a short time, a day or two, and then it fades away. And a neutrino pulse must have been made then, but of course we didn't know. It went right through us all, but it would have been quite a flash of neutrinos that went through us, but of course nobody felt it. They wouldn't interact in you, but detectors would have gone crazy. And these big detectors are hoping another supernova will happen soon, but not too close, okay, but much closer than supernova 1987A. This is a Crab Nebula, and now one can zoom in to the center and see that in the side there is the remnant of the supernova, which is a spinning star that is actually emitting radio pulses, and called a pulsar. It was discovered. Anyway, I won't go more into that story, but here's other pictures of beautiful supernova remnants in the sky. Some of them are, you see the left, a beautiful spherical shell, and on the right there's one that's more turbulent, twisted around and up. But I put on the top right there APOD, stands for Astronomy Picture of the Day, and you can download the app, and every day you can go in and see the astronomy picture of the day, and every day they put something, a picture from the sky of something interesting. So for days I was looking every day at that, but it's every day, so many things. So this is now, to put a bit of humor into this, can you read the caption? I meant to put it in bigger, but it reads, it's somewhere between a nova and a supernova, probably a pretty good nova. So, Spencer, he's a great cartoonist. So this is the remnant of the supernova that was seen in 1987, called 97A. It's in a nearby galaxy called the Large Magellanic Cloud, which was discovered by Magellan. You see it from the southern hemisphere. It's a nearby galaxy, and the supernova exploded in then, and it was briefly visible to the naked eye on a dark, clear night, I think. I never saw it, but this is an image in different wavelengths, and on top you see sort of superposition, and you see the ring of expanding matter that had been blown off from the supernova, and from turbulence reasons it forms a sort of ring. There's a video that I don't think I'm able to put in here that you can see it. There's a link there. And when this is on YouTube later, you'll be able to take your time and look at that, I suppose. Or maybe this will work, actually. I wonder if this works. It is a video. I don't know how I can make it go. I might have to. Let me just try it. Super expert at putting videos in these talks, but that's it. Oh, maybe it works. There is sound, but you probably won't hear the sound. The sound music goes with it, and it's very beautiful. Just about hear the music. This is not actual observation, but it's a computer reproduction of what should have, could have, would have happened. This one was seen in 1987, but it came from a nearby galaxy, which is about 100,000 light years away. So it actually happened 100,000 years ago, but we saw it in 1987 because it takes a long time to get here. And this is how those rings, bright spots, formed by turbulence. So that was a little video from NRAO, and if you see it on YouTube, you can actually listen to the music. Great. So here's a picture now of this, now as it is now, okay, with that ring and a couple of some stars in the background. But there were neutrino telescopes, vast tanks of water, which detected some neutrinos from that supernova. You see on the right that plot of over time, the number of neutrinos they detected, and then they suddenly saw this burst. 13 neutrinos, well, actually there were 35 altogether, 3 or 4 different neutrino telescopes, tanks of water or ice, saw it actually, it detected those neutrinos. So we detected neutrinos from a supernova, which is super interesting because they come out from when the supernova collapses down towards the end result, which is a spinning pulsar. The neutrino flash comes out, and it comes through all the material, which light doesn't come out. So the light comes a little tiny bit later than that. So then, Paul. Good question. So, all the elements like carbon, nitrogen, oxygen were not made from the Big Bang. They were made in exploding stars. And at the very beginning, the Big Bang, when that started, before there were galaxies and stars, after the Big Bang, there's only hydrogen, helium, and a little bit of lithium, element 3. No other elements. So the carbon, nitrogen, which is less safe for life, did not come from the Big Bang. Stars were formed from fluctuations in density. Stars were formed, and when the stars then burnt up and collapsed under their gravitational field and exploded as supernova, then the helium and were fused to form heavier elements in a runaway thing, creating energy. Because when you fuse 2 light elements to heavier ones, they release energy. And that was it. So, and then other stars were formed later. So the sun is probably a 3rd generation star or 4th generation star. And all our carbon, nitrogen is made in supernova explosions. So that, in fact, in that ring here, there will be, actually, I'm sure they have looked at the spectra, and you can see nitrogen, oxygen, carbon, and so on produced in that supernova. I'm not sure of the details of that, but I'm sure they have done this. So you need a big target to see neutrinos. So you look at a big transparent mass. So there are basically successful types under sea. This is Antares on the left. You see strings of the light detectors being anchored on the seabed, coming up in a clear part of the sea where the water's clear enough to transmit light, and you look for cases when several of those photomultipliers see flashes of light at the same time. And on the right you see a thing called KM3 net, 3 cubic kilometers of water. And there are 3 of these in the Mediterranean, one off France, one off Greece, and one off Italy. That combine themselves. So when one sees some flashes of light, the others look to see if they see it too, and the astronomers may tell them, oh, there was a supernova that happened. But, and then here is now the granddaddy of these detectors. It's called IceCube. It's in Argentina. So in Argentina, South Pole, it's by the South Pole, you've got the snow, and then under the snow is ice, and it goes ice down for 3 kilometers or so. And it's pretty clear down there because, so they have amazingly instrumented a cubic kilometer of ice with photomultipliers down in the ice to look for flashes of light in the ice from neutrinos. How do you get those photomultipliers down there? Any ideas? It's a clever trick. You make lots of hot water and you melt a column of the ice and you push hot water down, you melt it, you make this. It doesn't refreeze quickly. So you make a column of water down for about 2 kilometers or more. While it's still water, you drop a string of photomultiplier detectors on cables down there, and then over a few weeks it freezes in. They're freezing in there. They're going to be down there until the Antarctic ice cap all melts or drifts away. And anyway, and they put a large number of these things there. You see, on the right, you see this surface station. This was actually started by a friend of mine called Francis Halsane at University of Madison, and he developed this. I think he ought to get this start of neutrino astronomy, very high energy neutrinos. So then at the top on the surface, you see the little surface building up there. It's of course small compared with the origin of this thing. Some pictures of this have the Eiffel Tower showing at the bottom of that, but it's a kilometer high. All this ice is amazing. And so this is just a representation of, on the surface, you see the surface building. And on the bottom, you see every spot there is one of these photomultiplier light detectors that saw a signal. And the color represents the time. So you measure the time, and you can get then the direction of the neutrino coming in. In this one, it's coming up from through the Earth, making these flashes of light. It interacts with probably the oxygen in the water to make a shower of particles, and then you get the direction of it, the time of it, and you figure out where the neutrino is coming from in the sky, and hoping you can discover point sources of ultra-high energy neutrinos in the sky. Right. So you figure out, from fitting all these tubes to signals, you figure out the direction it came and the time, and they're coming through it almost. No, you can't tell the distance, you just come the direction. So you say, where did that come from in the sky? And you plot it on a map of the sky to see if you can see where they came from. And because neutrinos aren't bent by magnetic fields, they tend to point back to where they came from. And they've done that. And here's a map of the sky. And there you see many neutrinos they have detected. And you see a dense spot or patch there on the right, which coincides with the position of a galaxy called NGC 1068, the Messier Catalogue of Galaxies. So they have now detected pretty convincingly neutrinos coming from that galaxy. And where they come from, this is cutting edge research, and one hopes to discover more of these things. But this sees neutrinos coming up through the Earth, so they're seeing the northern hemisphere, in fact, better than the southern hemisphere, because it's better shielded from cosmic rays down there. So maybe there's an artist's impression of a black hole in the center of this galaxy that could be accumulating, so gas and dust and even rocks and planets and stuff spiraling into this massive black hole in the center of that galaxy. And as they do so, they radiate enormous signals in X-rays and gamma rays and neutrinos. So probably that patch of light of neutrinos that they see from NG, from that galaxy, is coming from the center of the galaxy, a supermassive black hole. So now we're starting to detect the presence of black holes with neutrinos. This is, okay, a busy technical slide, but you see the energy scale from left to right. Every tick is one factor of 10 in energy. And I put it here because the cosmic rays are down at the lower end. They're cut off. Actually, they're cut off at the top energy spectrum by those cosmic rays hitting the microwave back. Never mind. There's a cut off there, and then the neutrinos and the cosmic. Sorry, I got it wrong. The cosmic rays on the right in the red, and they're cut off by a cutoff. Those cosmic rays are hitting the microwave background and being attenuated. In the middle, you see neutrinos, and down there on the left, you see gamma rays. But here's a famous event from a blazar. A blazar was an event that was brighter than all the stars in the galaxy, in its galaxy, optically, seen in X-rays, gamma rays, and in neutrinos. This is one neutrino event from IceCube. You see hundreds of photodetectors saw a signal. You've got the direction it's coming up through the Earth and pointing back to this event that was seen by gamma ray telescopes and so on. So it's multi-messenger astronomy. This is a cubic kilometer of Antarctic ice. And this picture, it's actually a video, and the link will take you to the video of gamma rays arriving in a space telescope for gamma rays called Fermi-GLAST. And the video shows them arriving one at a time. And the size of the ring is the energy of the gamma ray that was detected. So that source is seen in gamma rays. That's the same source that neutrino came from. That's a link to it. So now, finally, I should talk about gravitational wave astronomy. And I put that picture in because my artist friend, Shanti Chandrasekhar, does a beautiful, I think, amazing abstract art inspired by science. I've been collaborating with her on exhibitions. I write about the science, she does the art. And gravity bends light waves. In fact, there's a thinking that gravity is not really like a force, like other forces like electromagnetism. It's actually just bent space or space-time, as Einstein showed. And mass bends space and it bends time as well, but that's another story. So here's a picture, a sketch of how the Hubble Space Telescope has seen directly mass-bending light. So what you see here in the sketch is Hubble telescope looking out to the right. It's looking at a galaxy in the foreground, and there's a galaxy way, way back. And the light from the galaxy way, way behind it comes to us through several paths, 4 different paths around that galaxy in front, which is bending the light and making multiple images of the galaxy far, far, far away. The distances says so. And here's a beautiful picture of what's called an Einstein ring. So it's the same thing. In the middle, you see that is a foreground galaxy. And the ring of blue light around it is actually the image of a galaxy way, way, way behind. And the light from that galaxy way, way behind, far, far away, is bent by the mass of the galaxy in front of it. And you see it bent around. It happens to be almost directly in line, so it forms a beautiful ring. It's like a lens. Gravity is a gravitational lens, if you like. It bends the light, but does that because space is bent by mass. And that's what Einstein said in his theory of general relativity. This was discovered in 2007 by the Hubble Space Telescope. We've seen more of these, but that's a particularly beautiful image. So gravitational waves. So when you have 2 massive objects spiraling around each other, the gravitational field far away is oscillating, and these are waves of bent space or bent space-time that propagate out at the speed of light and shake space and time. So when a gravitational wave passes through us, we're stretched in one direction or squeezed in the other, and then opposite, it's called a quadrupole. And these have been sought for a long time. Einstein sort of predicted them, but didn't think they could ever be discovered. But this is an amazing now gravitational wave telescope. You see in the top left, it's 2 vacuum tanks arms, 2 pipes with vacuum in, and laser light is split in 2, sent down each arm at 90 degrees to each other, reflected back and forth many times, actually. And when a gravitational wave will pass through, that one arm is stretched and the other shrinks, and vice versa. So they do that with the frequency of the gravitational wave. Now, there are the main 2 of these in the US are in Hanford and Livingston. You see the locations of them there, far, far away. And 2 is quite important because the vibrations are so tiny, 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 they happen all the time, just noise. But when 2 detectors like that see the same pattern at about the same time, you can say, well, that probably had to be a gravitational wave passing through. So these are incredibly technical things because you won't believe this, but those 4-kilometer arms are stretched and shrink by less than the size of a proton, which is 100,000 times smaller than that hydrogen atom. How can you detect that? It's just incredible, amazing, because you have many. Anyway, what was the breakthrough here was they detected these two gravitational wave telescopes, if you like, detected a chirp. You see the wavelength pattern in the top left of these two detectors, and they match. And the oscillation rises in frequency. It's called a chirp. It goes like that. As the frequency goes up, it happens the same way in those two places. Not exactly the same time, because the gravitational wave takes a bit of time to go between the two telescopes, so you can get some sort of direction from that. But then it turns out the only explanation for this was two massive black holes spiraling around each other, and as they do so, they shake up space and radiate waves of gravitational waves and lose energy, and then eventually they crash into each other and merge to one black hole. And in the process, they radiated away so much energy, which is so much mass, that the mass of the black hole they form is a lot less than the mass of the two gravitational waves you started with. All that mass is converted into energy. And the energy output, briefly, is more than the energy output for all the stars in the visible universe. Just briefly, the second as it happened. So that was a breakthrough, actually, in detecting the gravitational waves. And that black hole merger was, I think, 10 billion light years away. So those gravitational waves have been coming to us from there. Dinosaurs became extinct. They were still not yet at the Earth. And here's another cartoon from Sidney Harris, and I have to read it. Astronomer saying to his assistant, "It's black, and it looks like a black hole. It must be a black hole." I'd say it's a black hole. Okay, now we've got time to read out a poem I wrote about this, but I can't read it from here, so I can, okay. More than 1,000 million years before dinosaurs roamed the Earth, a ripple in space spread through the universe. Traveling at the speed of light, it had covered most of its journey to the Earth when the dinosaurs became extinct. Spreading in all directions, getting weaker all the time, those gravity waves arrived at Earth. For a fraction of a second, they passed through us all. We were stretched in one direction and squashed in the other, then the reverse, like wobbling jelly, unfelt by all the waves of excitement, elation among the watching scientists. Such a tsunami in space-time, caused by two black holes spiraling around and crashing into each other, the energy emitted momentarily more than that of all the stars in all the galaxies in the universe. One black hole had formed from two. It rang like a bell, shaking space and time before settling down quietly, ready to swallow stars down to its central singularity. Actually, I don't believe there's a singularity in the middle of the black hole, as Bob Anderson knows, but anyway, that's my theory. So now we've discovered many more of these things, and here you see, it's already about 2 years old, but what you see here, look at the top, you see two black holes merging into becoming one, supermassive ones, and then all these others we have detected since then. There's now two more new gravity waves telescopes around the world, and they can all see being shaken up by this thing. And then lower down we have neutron stars merging together. Neutron star is a collapsed star. It's not a black hole yet, but it's like a giant nucleus with all the protons and neutrons squashed together, and the protons have been squashed with electrons to become neutrons. So now this is opening up a whole field of gravitational wave astronomy. And there's a new project to go up in space called LISA, which is on the cards, and it has 3 detectors spaced apart, floating in space by something like, 1,000 kilometers apart, and they look for gravitational waves coming through, and they're going to detect thousands of these objects, and that's an exciting project for the future. So this is now a sketch, as if space was two-dimensional. If it was two-dimensional, then the geometry in the black hole, it gets bent down but really space is three-dimensional, so this is just a sort of sketch, but three-dimensional space can be bent like that, as Einstein had shown with his theory of relativity. And so many people think that at the end of the black hole, Stephen Hawking said it should eventually evaporate away when the universe becomes very cold and end up in a singularity. Or I think maybe that's not quite right, but I call it a Planck-on, which is that time and distance, like you can read the number 1.616 10 to the minus 35 meters across, and the mass is 21.76 micrograms. I vote for B, but Bob Anderson knows about that. So then I'm about at the end. So we live in incredibly exciting times, exploring the universe and opening new windows on the sky other than electromagnetic radiation. And this is a picture from the Hubble Ultra Deep Field. The Hubble telescope in space stared, it's a huge digital camera, right? Huge digital camera this size, and it stared at one patch in the sky about the size of a grain of sand at arm's length. And it did an exposure of days and days and days. And that is a picture that it got where there were no stars in our galaxy there. It's looking between any stars in our galaxy, much smaller patch than the moon. And what you see there is everything in there is a galaxy, a distant galaxy. And because that patch in the sky is so small, and you've measured in that picture how many, like 10,000 galaxies in that patch. So you multiply the whole area of the sky, and you say the visible universe all around should have something like 100,000 million galaxies. And each galaxy, we think, has something like 10,000 million planets, or stars and planets, and we thought we were the only one, but now we know we're not just the only one. And maybe our universe is just one out of gazillions and gazillions of universes. That's another story. So here's a final sketch, which is I've seen out to the limits of the observable universe, and believe me, it's no better out there than it is here. And finally, to read this. So I'd like to read it, but I don't want to lose the microphone. Can you read it? Okay, you read it. Paul. The best event is this blazar that I said. Now that wasn't seen it was seen with that neutrino event in Ice Cube. It was seen in gamma rays and X-rays, and visible as well. I don't know that it was seen in radio waves or microwaves. I'm not sure if it was. Microwave astronomy I didn't really mention, but microwaves were found to come from the sky. They looked at the whole sky, and there's patches of the sky, and they show the universe as it was at the age of 300,000 years. But that is a different story. That's a cosmic microwave background. But that's a different story. So hopefully in the future we will see more of these ultra-high-energy neutrino events. Actually, Ice Cube, I didn't show this, but they've looked at lower energy neutrinos, and they can see the shape of the galaxy. They've measured lots of neutrinos from the galaxy, not so high energy as this one, from our galaxy, the Milky Way, yeah. Milky Way. Yeah, more questions. Sorry? Yes, I did, actually. It was odd, because, well, the story there, I was at CERN, I happened to be at CERN for other reasons, and he happened to be there giving a talk in the auditorium. Now, of course, there was a queue outside hours before. You couldn't get into that. But actually, I'd seen him before. Anyway, what happened then, I couldn't get into it, but I had seen him give a talk at CERN before. He couldn't give a talk, but he's there and his computer's giving a talk for him, you know. But this one, I sat outside that evening after he'd given his lecture, and he came out having a drink outside in the cafeteria terrace. He came out with his wheelchair and his nurse and his retinue, and I said, "Carpe diem, seize the day." I went, they were looking for a power for his computer, so I helped them with that, and I sat down and I said, "I wonder if dark energy's got something to do with tachyons." And of course he didn't react at all. But one of his bright young men, he gathered very bright young men, said, well, that would make the universe unstable, because he thought about it. And my reaction was, well, if the universe is blowing itself apart, that looks like being unstable. Okay, that was the end of the conversation. But I talked to him, he didn't talk back to me, but and then the follow-up is that I was waiting for my daughter, who lives in Geneva, to arrive with my grandkids, and she came up there. I was still sitting with him. I greeted her, "Hi, Isabel," you know, hug, and went off. And afterwards I thought, I hope he wasn't composing an answer to me, and then I walked away before he'd finished composing his answer on the computer. I thought, no, I'm sure they would have stopped me doing that if they had known he was doing that. But anyway, that was my one Stephen Hawking story that I had. But yeah, I don't miss a chance to talk to people if you get a chance. Don't be shy, you know, like, and Feynman I've talked to as well. And anyway, but Stephen Hawking, yeah, that was very special. Bob. Good question. Actually, yeah, Bob. So there is the cutoff in energy from that would be above the cosmic ray energy cutoff, but there is a thing in the cosmic ray neutrino spectrum where this is very interesting. Neutrinos came from the Big Bang, we think. The whole sky is full of these very, very low energy neutrinos from the Big Bang. Now, one of these ultra high energy neutrinos can, in principle, interact with one of these low energy neutrinos from the Big Bang, and neutrinos, actually neutrino and antineutrino, can merge to form a Z boson, which could then decay to electrons or muons. So that happens at a very special energy corresponding to the mass of the Z boson. So it should cause a dip in the neutrino spectrum at that energy, which we can predict very well, the energy. It's just kinematics, but that's not been detected yet. But that would be really interesting. It's called the glacier resonance, I think it's called the glacier resonance. So in principle, neutrinos, ultra energy ones, will interact with the Big Bang neutrinos and get absorbed, but then above that energy, they're still okay. So, yeah. All right. Yes?
My question is probably going to show my ignorance, so stay with it. It seems like we're collecting a lot of energy from the sun. If I understood you to say, was this huge mass of low energy gone by the Earth and all that. Any research being done on how do you collect that in some way to make use of it?
Do you mean in solar wind coming to the Earth, or
Whatever it is,
well,
how in some way can you make use of that on the same way that we make use of the sun?
well, the energy, I think the energy per square kilometer coming to the sun in the form of this wind is much less than the energy coming in the form of ultraviolet and heat and so on. So I don't think it would be a useful source. I don't think so. But it's spread all over the place, right? So when, you know, the aurora, for example, it's spread over square kilometers, so it's not exactly concentrated. It's also very variable. Now, there's one thing which I didn't mention, but on the slide, it said coronal mass ejection. So sometimes the sun burps a huge blob of ionized gas in the solar wind, and it happens every so often when the sun's very active, and usually it misses the Earth. Fortunately, in 1856 or so, it didn't miss the Earth. We had telegraph communication between DC and New York, and the telephone operators got electric shocks because of this flash of this burp of ions that hit in the atmosphere. Now, that's going to happen one day. I mean, it happened not long ago, but missed the Earth by a few days. But when it happens and hits the Earth, we had better be prepared, because that would give such an ionizing atmosphere, it could bring down all communication. Satellites, aeroplanes might lose their ability to fly, remote. So it's very important, I think, to be monitoring this closely, because we get at least some hours warning, and astronomers could say, watch out, there's a coronal mass ejection could be hitting the Earth, land all the planes, controlled turning down of power stations, because when this thing hits power cables, it could give blackouts that could be ages to fix, so it's a very serious thing. It might not happen for 100 years or 200, but it will happen one day, and we better be prepared for it. And there's a solar observatory orbiting the sun, the Parker Solar Probe, which is monitoring it. But it's very important that we don't say, oh, science, we don't need these things anymore, so, because it could save, imagine all the power going down in the US for months while we try and fix all the broken stuff. So, but I don't think we can utilize these cosmic rays for giving us power. We can use the sun. By the way, we're trying to build a fusion reactor on Earth to use those reactions in the sun to make power on Earth. We're not really using the reaction of the sun. We're using deuterium and tritium, which is not happening, not the main thing as sun. But it's always years away, these fusion reactors, and I think we've got a steady fusion reactor on all the time, safe distance away, it's called the sun. So we can use that, okay, the sun doesn't shine at night. Yes, it does. It just shines on the other side of the Earth, but with batteries and so on. Anyway, solar power is a key element, I think, of energy in the future. And personally, I wouldn't buy shares in fusion power stations like Tokamak. They're sort of, they've shown they can get fusion on Earth for like a microsecond by imploding a pellet, and they can do it once every 6 months, and they get enough energy to boil a kettle or something like that out of it. But don't hold your breath for fusion reactors. But any other questions? Oh, yes, Dan.
Mike, I wasn't around then, but I recall somewhere at the end of the 19th century, scientists, astronomers thought that they had learned all there was to know about it. Was some, am I dreaming about that?
No, it's...
They thought that, you could see up with telescopes, but with telescopes, it would all be over. That's all we have.
Right, I should repeat the question. I should have been passing a microphone around, but the question was, at the end of the 19th century, many physicists were saying, this is it, the end of physics, we just have to measure more decimal places, and that's it, we've found everything basically. And in 1896, 1897, we discovered X-rays, radioactivity, that was so arrogant to think, and even not so long ago, Stephen Hawking was saying maybe the end of theoretical physics is in sight, we'll maybe understand everything at the level of fundamental physics. I mean, he was wrong, of course, about that. There's so much stuff out there. Astronomers say there's dark matter. I didn't have time to talk about it, but Vera Rubin, great woman astronomer, should have got a Nobel Prize for this, but she didn't. She and her colleague Kent Ford found there's more mass in the galaxy than we can account for in stars and planets and gas and dust because of the rotation of it's holding it together. It's called dark matter. There's 5 times more of that stuff than there is of the matter we know. But we only know it from astronomers, from gravity. And we think it's made of particles we haven't yet discovered. And that's what we're looking for. We haven't found them yet. But we believe it's probably particles we haven't yet discovered. Maybe they're too massive or too weakly interacting. Or maybe they're little lumps of rock or dust or something like that. But it's dark matter. And then there's dark energy, which is the elephant in the room. Because the energy in the universe, 70% of it is dark energy. And that is causing the universe to blow itself apart faster and faster and faster. And we don't know what that is. Bob knows I've got ideas about it. Yeah. Oh, at the back of the room, yeah. Could you, if you have a question. Oh, I see. All right. So that's it. Thank you very much, folks. Next month, we have one second Sunday in January about optical astronomy again. Thank you.